Hello, everyone. Welcome to the first session of Beyond Bohm, Science, Order and Creativity, Physics and Metaphysics. Thank you all for coming. This is a great turnout. I'm James Barbieri. I'm the Associate Program Director at the PARI Center, and I'll be your host for today. As a host, I'm here to help you throughout the whole call. So any problems, technical or not, feel free to just drop me a message in the chat. Before we begin, I'd just like to remind everyone of a couple of Zoom rules. First of all, we ask participants to turn off their microphones during the presentation and Q&A, just to ensure a good quality audio. For this reason, we may mute you if you hear any background noise, but this is not to silence anyone, it's just to ensure the good audio. But at the same time, we do encourage you all to turn on your camera, since everyone's faces and reactions creates a nice, inclusive education environment, trying to make it like the real thing as much as possible. During the Q&A and discussion, if you want to ask a question, or you can use the raise your hand function, which can be found at the bottom of your screen under reactions. Otherwise, if you can't find it, you can physically raise your hand, and if I spot you, I'll call out your name and you can ask a question. If you do feel shy, however, you can ask your question in the chat and I can read it out for you. The chat will be open throughout the call, so do feel free to use it, as it's a great way to exchange ideas during this session. Finally, all sessions are recorded for archival purposes and for you all. The recording will be uploaded to Vimeo 3 days after the session, so you should all receive the link to this recording. If you don't get it, drop us an email and we'll sort it out. Okay, so now we can begin this session. So this is Beyond Bohm, Science, Order and Creativity. The PARI Center has a very close connection to Bohm. David Peat, the founder of the PARI Center, and my grandfather had worked with David Bohm for many years. Since Bohm's passing, Peat continued his work by founding the PARI Center, which, amongst other topics, has the mission to spread the work of David Bohm, work that was not popular amongst the scientific community at the time. With the turn of the 21st century, this seems to have changed. Bohm's interpretations of quantum mechanics are now one of the prevalent interpretations, with many academics discussing and moving forwards with his work. With this series, we have invited esteemed physicists, mathematicians, philosophers, and artists who are actively working on these ideas and looking at where these ideas could lead us in the future. As you may know, this is the first session of the first part of the David Bohm event. While in the next part, in August, we'll be looking at Bohm's thought and philosophy. During these 3 weeks, we'll be looking at Bohm's most notable contribution, his physics and metaphysics. And now to start our exploration of where Bohm is today, we have the honor of introducing Emily Adlam. Emily is a theoretical physicist and philosopher of physics who studies the foundations of quantum mechanics and quantum information. She received her PhD from the University of Cambridge in relativistic quantum information and has recently published a book entitled Quantum Foundation, which is part of the Cambridge University Press Elements of Philosophy series. Today, Emily will talk about contextuality in the Broglie-Bohm and beyond. And with that, I'll pass it over to you, Emily. A very warm welcome from all of us.
Great. So it's lovely to be here with you all at this lovely event in celebration of the life of Bohm, who was an extremely forward-thinking and wide-ranging physicist and whose ideas are increasingly important in my own field of quantum foundations. So what I'd like to talk about today is the phenomenon of contextuality, and in particular, how it relates to the de Broglie-Bohm theory, and why I think this is a particularly important argument for the de Broglie-Bohm theory. So I'm going to start by explaining a little bit about what contextuality is. It's quite common in discussions of quantum mechanics to give various lists of ways in which the quantum world is interestingly different to the classical world, and contextuality is one of those things that often comes up in these discussions. And thanks to a lot of interesting recent research, we now have a really good understanding of the mathematical structure of contextuality, of the limits of contextuality within quantum mechanics, and also the way contextuality behaves in generalized probabilistic theories. But the conceptual implications of contextuality and what exactly it means for our understanding of reality and of the quantum world there's still work to be done there. There's still quite a lot of discussion and debate on these issues. So I'm going to mention a couple of things that people commonly say about contextuality and explain why, in my view, these things are actually not correct and are somewhat obfuscating the issues. I'm then going to introduce what I personally believe to be the correct way to think about contextuality in terms of fine-tuning effects. I'll then discuss various possible ways in which we might explain the existence of fine-tuning in quantum mechanics. And finally, I'll argue that the de Broglie-Bohm actually has a very strong explanation for this phenomenon, and indeed a much better explanation than any of the other mainstream interpretations. So I'm going to suggest that this is in fact a particularly strong argument for the de Broglie-Bohm interpretation over various other possibilities. So to start off, let's talk about the ways in which quantum and classical measurements differ. So when I make a measurement in the classical world, when I say I measure the size of some table and I find out that it's 3 by 2 meters, I take it that I have established a definite property of the table that was a property before the measurement and will continue to be a property after the measurement. So the measurement is understood to just be observing some fact that is not brought into being by the measurement and is independent of what measurement I chose to make. So given that classical picture of what measurements are doing, we would expect that for any classical system, we can make a list of what properties it currently has, and we can use that list to determine what the results will be of any measurement we might subsequently choose to make. Now, we can represent that procedure mathematically by making a collection of all the possible measurement outcomes that could be obtained from some measurement on the system, and then assigning the values 1 or 0 to each possible outcome, such that every possible measurement has exactly one outcome with value 1. The idea being that the outcome with value 1 is understood to be associated with a property that the system currently has, and thus that's the outcome that will definitely occur if we perform that measurement. Now, clearly, if it is the case that every measurement outcome occurs in only one measurement, then it's always trivial to make this assignation, and we'll never have any problems there. But in quantum mechanics, measurement outcomes are typically represented by positive operators, and measurements are represented by sets of positive operators which sum to the identity. And it's quite straightforward to show that that means that in dimensions of greater than 2, in general, a quantum measurement outcome can occur in more than one different measurement. So what that means is that we could, for example, have one measurement with outcomes A, B, and C, and another measurement with outcomes A, D, and E. So if quantum measurement outcomes are like classical measurement outcomes in the sense that they correspond to definite properties of the systems that exist prior to the measurements, then we would naturally expect that if, say, I perform the first of those measurements and I obtain outcome A, it's also the case that had I instead performed the second measurement, I would still have obtained outcome A. A is to be understood as a property of the system, which I'm just finding out about in my measurement. So note that in quantum mechanics, measurements in general disturb the state of the system. So unlike in classical mechanics, we can't perform all the possible measurements. In general, we can only perform one measurement. And if we perform subsequent measurements, the result will not necessarily be the same as it would have been if we'd started with that measurement. So we have a range of possible measurements we can make. We're only going to be able to perform one of them. So assuming that quantum measurement outcomes are like classical measurement outcomes in the sense that they're associated with definite properties, then we would expect to still be able to make this assignation of values 1 and 0, such that in our set of quantum measurements, every measurement has exactly one outcome with value 1, even though now it's sometimes the case that certain outcomes may occur in more than one measurement. So the Kochen-Specker theorem is a seminal result of quantum foundations, and it is a proof demonstrating that that we can create collections of quantum measurements where it is not possible to make this mathematical assignation of values 1 and 0. So that is to say, we will inevitably end up with a situation where, given some assignation, we are guaranteed to get the result A to some measurement, And then we are also guaranteed to not get the result A to some other measurement, even though A is a possible result of that measurement. So we're no longer able to just regard A as being a property that the system does or does not have. What we find is that whether we get the result A or not depends not only on the current state of the system, but also on what we refer to as the context of measurement, which is to say what the other possible outcomes are of the measurement we're currently making. So for that reason, we say that quantum mechanics exhibits contextuality because measurement outcomes sometimes depend on the context of measurement. Likewise, we say that classical mechanics is non-contextual because we never need to have measurements depending on the context of measurement in this particular way. So some physicists have responded to the Kochen-Specker theorem and these types of proofs by saying that, well, if quantum measurement outcomes can't be straightforwardly associated with elements of reality, perhaps we should just give up on supposing that quantum mechanics describes reality at all, and we should just suppose that the quantum mechanical theory is just an algorithm for making predictions and isn't saying anything about reality. Now, I personally and many other physicists, including, of course, Bohm himself, find this approach fairly unsatisfying. First off, it just doesn't really, it doesn't really answer one's curiosity about what's really happening. And moreover, simply refusing to answer questions about what's really going on underneath doesn't seem like a particularly scientifically useful route to take. It doesn't lead us anywhere interesting. Whereas, as I hope you'll appreciate later, trying to answer these questions does sometimes lead into really interesting places and will hopefully contribute to the future of science. So for that reason, I don't think anti-realism is the right response to the Kochen-Specker theorem. And moreover, it's certainly not the case that the Kochen-Specker theorem forces us to abandon realism. It only disproves a fairly naive form of realism where it is supposed, where the mathematics of the theory is taken entirely literally, and it's supposed that every unique mathematical object in the theory must be mapped to a unique object in reality. So for the realist, the natural response here is to say, well, clearly the relationship between the mathematics of the theory and reality is a little bit more complicated than we might first have supposed, but we can nonetheless find out something about reality by examining the mathematics. However, the story of contextuality does not end there, because some years later, Spekkens came along and posed the question, can we come up with some generalized notion of contextuality which doesn't assume determinism and which doesn't make this fairly rigid assumption about the relationship between the maths and the reality? So to come up with this generalization, Spekkens used a framework that he developed, which is sometimes referred to as the ontological models framework. So in Spekkens's framework, we associate each quantum system with what's known as an ontic state, which is meant to represent the true underlying state of the system at the given time. So the ontic state might, for example, be the same as the quantum state, but it might also include more information than the quantum state or less information than the quantum state. And so the idea is that it's these ontic states which mediate the relationship between preparations and measurements. So in particular, with every possible preparation, we associate a probability distribution over ontic states. And this distribution assigns to each state lambda the probability that we will obtain that state when we perform that preparation. Likewise, with each pair of measurement M and outcome K, we have a response function, and this response function assigns a probability to state lambda, which represents the probability that if the system is in state lambda and we perform the measurement M, that's the probability that we'll get the result K. So we can use the ontological models framework to kind of reproduce ideas about what the mechanism underlying quantum mechanics and what is really going on underneath all the quantum apparatus. So using this framework, Spekkens defined a generalized notion of contextuality based on what we might call the ontic equivalence principle. And that's the idea that procedures which are operationally equivalent, that is, which give rise to the same measurement statistics, the same operational statistics at the observable level, should always be represented by the same object in the ontological model. So that idea leads to two different forms of contextuality or non-contextuality. We say that an ontological model is preparation non-contextual if all preparations that prepare the same quantum state are represented by the same probability distribution. And that's because the same quantum state will always give rise to the same subsequent operational statistics. So by the ontic equivalence principle, we would expect that all such preparations would give us the same distribution over ontic states. Likewise, we say an ontological model is measurement non-contextual if a given quantum mechanical measurement operator is always represented by the same response function. So that is to say, a given outcome will always be represented by the same response function, even when it's appearing in different measurements. So that allows us to understand this form of non-contextuality as the generalization of the Kochen-Specker idea, which said that, again, measurement outcomes should look the same in different measurements and different contexts of measurement. So using these definitions, Spekkens was then able to prove that there is no preparation non-contextual ontological model for quantum mechanics. And moreover, if we assume outcome determinism, there's also no measurement non-contextual ontological model for quantum mechanics. So what that means is that even if we move away from this very naive idea about the relationship between math and reality, we still can't get away from contextuality. We will still end up with these situations where objects which are operationally equivalent have to be represented by two different objects within the ontological model, the representation of reality. So this feature of quantum mechanics is really a very deep one, which is built into the structure of quantum mechanics and really isn't going away. So the question that we're now left with is what conclusion should we draw from all this? What is contextuality really telling us about the world? And the first question to be addressed here is really, what exactly is wrong about contextuality? Many physicists have the intuition that there's something a bit weird, something a bit problematic about it, but actually articulating what is wrong with it is by no means trivial. So I'm going to talk now about a couple of suggestions that people have made in this connection, and I'm going to argue that several of these things that people say are actually not correct. So first off, it's common to say in the literature that contextuality is problematic because it involves violations of Leibniz's principle. So Leibniz was a contemporary of Newton. He made a number of important contributions to physics, maths, and philosophy, but he's particularly well remembered for what's known as Leibniz's principle of the identity of indiscernibles, which is the statement that if for every property F, object X has F, if and only if object Y has F, then X equals Y. So that is to say, Leibniz's principle says that if two objects have all the same properties, then they are one and the same object, they're identical. So Leibniz's principle is a thesis about the nature of numerical identity. It's about what it means for two objects to be identical. Now, you can sort of see why people think that contextuality might have some relation with Leibniz's principle, because, of course, the problem with contextuality is that we have two objects which seem to have all the same operational properties, but which nonetheless are not identical at the ontic level. So there's some kind of similarity of structure here. But in fact, I don't think this is a correct application of Leibniz's principle because, as I say, Leibniz's principle is supposed to deal with numerical identity. And the kind of identity we're dealing with in the conceptual case is not, in the contextuality case, is not numerical identity. Rather, we're concerned here with sameness of kind. So, for example, if I perform two different quantum mechanical preparations of the same quantum state, there's no question about whether those preparations are numerically the same thing. We know that they're not numerically the same, that they involve different procedures, they take place at different places at different times. So the question is not, are they numerically identical? It's, is it reasonable for us to suppose that they are not represented by the same kind of process at the ontic level? So for that reason, Leibniz's principle really isn't the appropriate piece of philosophy to call on here. Moreover, Leibniz's principle is usually regarded as being a conceptual truth about the nature of identity. This is what it means for two things to be identical. Whereas whatever contextuality is about, it's not, whatever the ontic equivalence principle is about, it's certainly not a conceptual truth. No one is saying it's logically impossible for two operationally equivalent things to be different at the ontic level. The concern is simply that maybe there's something a bit epistemically problematic about that. So again, this conceptual truth about the nature of identity isn't really the right principle to call on in trying to make sense of contextuality. And I want to reinforce that this is not sort of just historical nitpicking, because invoking Leibniz's principle in this regard is, I think, really obfuscating what is actually going on, because, as I say, Leibniz's principle is supposed to be something that we just know to be true as a consequence of the meaning of identity. So when someone invokes Leibniz's principle, it kind of looks like, well, that's the end of the story, there's nothing more to be discussed. Whereas, in fact, whatever's going on with contextuality, it's certainly not a conceptual truth that the ontic equivalence principle must hold. It's not true as a matter of logic, and indeed it had better not be true as a matter of logic, because it does seem to be violated in our world. So invoking Leibniz's principle here is, I think, not only historically wrong, but also not good science, and is leading people to misunderstand the issues at stake here. It's also reasonably common to invoke Einstein's argument in this connection, and in particular, people I want to quote Einstein's saying that we should try to rid our theories of asymmetries which do not appear to be inherent in the phenomena. And again, you can see how one might think this quote is related to contextuality, because the idea is that when we have two different ontic representations of what appears to be operationally the same thing, that is an asymmetry in the ontic representation, which doesn't appear to be inherent in the operational phenomena. So Einstein originally made this comment in his 1905 paper on special relativity, and the asymmetry he was referring to was absolute space. His concern was that there's no possible way to observe the difference between being at rest relative to absolute space and being in constant motion relative to absolute space. And thus, the existence of absolute space in our theory introduces an asymmetry which is not inherent in the phenomenon. And in fact, we can just remove absolute space from our theory without losing any of the empirical content of the theory. And so, by an application of Occam's razor, it seems like we should get rid of absolute space. And that, of course, is exactly what Einstein did in that paper. However, the contextuality case is not really like this. And the reason for that is that we have all these proofs of contextuality, the Kochen-Specker theorem, the Spekkens theorems, and so on. We have a number of proofs which make it very clear that we can't simply rewrite our theory to get rid of contextuality. It really is a built-in part of the quantum phenomena. And thus, although we may have an asymmetry here, it's not an asymmetry which is not inherent in the phenomena. It is very much inherent in the phenomena. So Occam's razor, there's no possible application of Occam's razor to the conclusion that we should just get rid of something. There's nothing we can get rid of here. So if this were really the motivation for people's concerns about contextuality, then we would naturally expect that the proofs of contextuality given by Kochen-Specker and later Spekkens would have been the end of this discussion. Whereas in fact, they've just been the beginning of the discussion. So I think it's pretty clear that there's actually some other motivation lying behind the concerns people have over contextuality. So to understand the nature of those concerns, it's helpful to think about how we might try to come up with some kind of model which doesn't seem to exhibit contextuality in this problematic way. So an example of this is Terry Rudolph's marble world proposal. And so Rudolph proposed a model in which every quantum mechanical measurement outcome is represented by a vector on a sphere, and the state is represented by something like a marble, which is lying somewhere on the surface of the sphere. And when we make a measurement, that's tantamount to presenting a set of vectors, and the marble will simply be attracted towards whichever vector happens to be closest to its current position. Note that each preparation is supposed to be associated with some probability distribution over initial positions of the marbles, such that we don't know for sure what the result of any measurement will be, because we don't know the exact position of the marble. So Rudolph's marble world proposal will still be judged contextual according to Rob Spekkens' definition, because if we try to write it in terms of response functions, we will find ourselves having to use different response functions for the same outcome in different measurement contexts. However, in a broader, more general sense, it does kind of look as if Rudolph's proposal is not really contextual, because after all, each measurement outcome is being represented by a unique object. And therefore we don't seem to have this problem of operationally equivalent things being represented by distinct objects on the ontological level. Moreover, it's pretty straightforward to see how the context dependence or the appearance of context dependence arises in Rudolph's model. Because of course, if the marble is being attracted to the nearest vector, then naturally which vector it goes to will depend on what the other possible choices are. It might be the case that the marble is closer to, say, vector A than to B and C. And so if we make a measurement with possible outcomes A, B, and C, we'll obtain the outcome A. But also the marble is also closer to vector D than to A. So if we make a measurement with possible outcomes A, D, and E, we will get outcome D instead. So that is an explanation for the kind of situation where we're guaranteed to get result A to some measurement, and we're also guaranteed not to get result A to some other measurement, even though A is a possible result of that measurement. So this all seems to work very nicely and makes contextuality seem very natural. However, there is a really big sticking point, and that's something that is sometimes referred to as Gleason's property. So Gleason's property refers to the fact that in quantum mechanics, the probability for getting a certain outcome to a measurement depends only on the state and not on the other measurements and not on the context of measurement. So that is to say, although we have to have dependence on context within ontological models, we never see that context dependence within quantum mechanics itself. So to make that work within Rudolph's model, to make the context dependence disappear, we would have to ensure that the probability distributions over positions of marbles that are associated with different possible preparations are very carefully fine-tuned to make sure that the context dependence exactly cancels out in every possible case, so that we can never actually observe this context dependence directly. Rudolph's model will only reproduce quantum mechanics if we use some very special, very carefully fine-tuned distributions to make sure that this context dependence exactly vanishes every time. And indeed, that's a totally general observation. No matter what kind of ontological model or reality underlying quantum mechanics we're trying to propose, it's necessarily the case that we have to choose probability distributions such that for any given ontic state, the probability distribution over outcomes depends on the measurement context. But when we average over ontic state, that dependence disappears. So the problem with contextuality really is not the context dependence itself. It's trying to have context dependence in combination with the disappearance of context dependence once we average over ontic states. It's this tension between context dependence in the underlying reality and no context dependence in the operational statistics. So Cavalcanti has made this observation formal. He used the framework of causal models to demonstrate that any set of experiments which violates the Kochen-Specker inequality, that is, which demonstrates contextuality in the original Kochen-Specker sense, must be represented by a causal model which is fine-tuned. And that fine-tuning is here being used as a term of art from the causal modeling framework, and it means that the parameters of the model have to be very carefully chosen so that different causal dependencies exactly cancel out, and we can't allow any small perturbations to the values of those parameters without losing without losing the effectiveness of the model. So to me, it seems reasonably clear that the best way to think about contextuality is not in terms of Leibniz's principle or in terms of Einstein's thinking about asymmetries, but as a problem with fine-tuning. The problem we have before us is to explain how this fine-tuning comes about, because it's both very precise and also weirdly conspiratorial. It's as if nature is deliberately trying to hide the context dependence from us so that we never see it in the operational statistics. For me, it's important that we appreciate that contextuality is a fine-tuning problem, because that then clarifies what we have to explain and what kinds of explanations might help make sense of the presence of contextuality in quantum theory. So I now want to talk a little bit about what sorts of explanations we might possibly give for contextual phenomena within quantum mechanics. But I first want to pause and observe that physicists talk about fine-tuning quite a lot. And various concerns have been raised about fine-tuning arguments in quantum mechanics and in physics more broadly. And I want to reinforce that the contextuality associated with that, the fine-tuning associated with contextuality is of a slightly different kind to the fine-tuning invoked in other parts of physics, and is, I think, rather more problematic and rather more in need of an explanation. So fine-tuning is often mentioned in physics with relation to the values of certain fundamental parameters. So, for example, people will say that the value of, say, the cosmological constant is much smaller than we perhaps thought it might have been, and this seems like a case of fine-tuning, and so we need some explanation for the smallness of the cosmological constant. Now, people have objected, and I think reasonably, that fundamental parameters do have to have some value. We don't have any very natural way to sort of form expectations about what values they are likely to have, and therefore it doesn't necessarily seem very reasonable to demand explanations for why fundamental parameters have one value rather than another. And I think that I have much sympathy with that view. But the contextuality involved, the fine-tuning involved in contextuality is not really vulnerable to that kind of argument because we're not dealing in that case with the value of just one parameter. We're dealing with the value of many parameters, which must all be very carefully adjusted to exactly cancel each other out all across the whole of space-time, the whole of history. So the fine-tuning here is much more widespread, and it also has this somewhat odd conspiratorial feature where it does seem as though all these parameters have been fine-tuned in such a way as to deliberately hide this effect from us. And so for those reasons, I think that even if you're not 100% convinced about fine-tuning arguments in physics in general, this particular instance of fine-tuning really is in need of explanation. So what kinds of explanatory strategies are available to us? One option, of course, is always just to accept the fine-tuning and say that's just the way things are. And this kind of route is pursued by the proponents of superdeterminism, which is a view that involves supposing that explaining quantum statistics by supposing that both the underlying states and also our choices of measurements are all carefully written into the initial state of the universe, and the whole thing is fine-tuned to produce certain surprising effects like non-locality in a way that is really quite classical but looks non-classical due to the careful fine-tuning of the initial state. So that's a route which is open to us. It would certainly be possible to explain contextuality in terms of the initial state of the universe being very carefully tuned in certain ways. But I think for me, that particular route is not very satisfying. Just saying that's the way things are doesn't really make the weirdness of the fine-tuning go away, and also doesn't seem to lead to any particularly interesting scientific routes for progress. The second option, which is always a popular option with any problem, is to deny that there is a problem at all. In that case, in this instance, the way to do that is to become an anti-realist, because an anti-realist will say, well, there is no reality underlying quantum mechanics, therefore you have no right to try and make ontological models representing that reality, and therefore there's no case that we can't even set up the problem with there being differences in the ontological models that are not reflected in the phenomena, because we're not allowed to have ontological models at all. So anti-realism certainly does solve the problem of contextuality, but as I said earlier, I find anti-realism both not very interesting and also not very scientifically useful. So that is also not a route that I find satisfying. So what options do we have for possible realist explanations? I see two main routes that we could pursue. So as I noted, Cavalcanti proved this fine-tuning problem using the causal modeling framework. So one thing we can do is appeal to existing knowledge within the causal modeling framework about how to deal with fine-tuning. And it's quite well recognized in that area of research that one way to deal with fine-tuning is to explain it in terms of equilibration effects. So the idea here is that we explain fine-tuning by supposing that the system starts out in some arbitrary state which is not fine-tuned, and then we postulate a dynamics such that as the system evolves over time according to its postulated dynamics, it will naturally move closer and closer towards the fine-tuning distribution, such that at the present time, the distribution will now look very fine-tuned, but we don't have to think of that fine-tuning as being some kind of weird conspiratorial effect that we can't explain. It's simply a consequence of the natural dynamics of the system. Option 2 is some kind of teleological explanation. So I use the term teleological here, referring to explanations which are in some sense goal-directed, or which allow the results of some procedure to explain why the procedure is the way it is. So that route would involve abandoning some of our ideas about the ways in which about time evolution and the ways in which we think of the past as always explaining the future. This would involve, we could move to some kind of picture where we have, say, the laws of nature applying all at once to the whole of history, and we could then apply constraints to the whole of history, which have the consequence that the relevant parameters have to be fine-tuned. So in that sense, rather than being weirdly fine-tuned inputs, those parameters then become outputs of the model, and their fine-tuned values are consequences of whatever constraint we have chosen. So I'm going to talk about each of these options more in turn, but in particular, I'm going to argue that the de Broglie-Bohm interpretation is a really good example of the equilibration strategy. So I'm going to therefore briefly digress and say a bit about what the de Broglie-Bohm interpretation is for anyone who might not be familiar with it. So I've spoken to quite a lot in this talk about various ways that we might try to understand the reality underlying quantum mechanics. And one way of kind of studying those questions is to use something like the ontological models approach, which allows us to ask very general questions about what the reality could be like. An alternative route taken by many physicists is to postulate some hypothesis about what that reality might be like based on our current understanding of the theory. And these hypotheses are often referred to as interpretations of quantum mechanics, because the idea is that they're interpretations since they don't make novel predictions, they're just supposed to reproduce the existing predictions of the theory. Now, as we'll see later in this talk, that's not really entirely accurate. At least one interpretation does in fact make novel predictions, and it's probably not the only one. So the term interpretation is not really ideal here, but I'll go on using it since it is the most common terminology in the field. So there are a variety of interpretations of quantum mechanics. You might have heard of the many worlds interpretation or the spontaneous collapse interpretation, and of course the de Broglie-Bohm interpretation, which I'll deal with here. So kind of one of the main tasks of an interpretation is to set out an ontology, that is to say what things there are in the world. And so the de Broglie-Bohm interpretation has an ontology consisting of both the quantum mechanical wave function, which evolves unitarily, and then also a set of identical point-like particles. And the idea being that the point-like particles have definite positions at all times, and follow continuous trajectories through space-time, but they are guided through space-time by the wave function according to the following guiding equation. So here qk refers to the position of the kth particle, mk refers to its mass, and psi is the in-particle wave function. So basically the idea of this interpretation is that our conscious experience and the macroscopic world with which we are familiar is understood to supervene on the particles themselves and not on the wave function. And so this explains why it is that our experiences and the macroscopic world is never found in a superposition, because the de Broglie-Bohm particles have definite positions always. They themselves are never in superpositions. But because they're guided by the wave function, and the wave function, of course, can be in superpositions, that makes it possible for us to see the various characteristic quantum behaviors when we perform measurements, even though the particles themselves and the things on which our experience supervenes can't themselves be in superpositions. So one criticism that some people have made of the de Broglie-Bohm interpretation is that it's concerning that the wave function has to play two distinct roles. So as I said, the wave function acts as a guiding wave, which pushes the particles through space-time. But in order to get the right empirical results from this interpretation, it's also necessary that at the beginning of the experiment, the de Broglie-Bohm particles are distributed in space-time in proportion to the distribution defined by the mod squared amplitude of the wave function. So the wave function both defines the initial distribution and also pushes the particles around over the course of the experiment. Now, prima facie, there seems to be no reason why the same object should play both of these roles. And some people have been concerned that it seems a bit suspicious or coincidental that it should be the wave function doing both of those things. However, the de Broglie-Bohm people have a really nice way of dealing with this problem. And their explanation is precisely what I have referred to as equilibration. So what the idea is that we can show that for nearly all initial distributions of the de Broglie-Bohm particles, in the course of temporal evolution, according to the usual evolution of the wave function plus the guiding equation, we can show that those particles will naturally move closer and closer to the wave function magnitude distribution. And thus, by the present time, their distribution will be sufficiently close to the wave function mod squared amplitude distribution as to be indistinguishable. So there have been various ways of demonstrating this. Durr uses the equivariance properties of the wave function evolution. Valentini uses a dynamical explanation akin to Boltzmann's H theorem. But both of them are essentially an equilibration explanation of the kind I have suggested. So therefore, we no longer have to see it as a strange coincidence that the wave function plays these two distinct roles. In fact, we see that the reason the wave function plays the role of defining initial conditions is just a consequence of the fact that the wave function defines the dynamics of the particles. Moreover, because this explanation is specifically an equilibration process, it also follows that we can immediately explain the contextual features of quantum mechanics, because the idea here is that at the beginning of time, when the de Broglie-Bohm particles were not distributed according to the wave function distribution, at that time, we would not necessarily have seen the same features. And in particular, the context dependence of measurements would not have been hidden in the same way. Some of some of the context dependence that occurs in the ontological models would really have been observable at the level of the operational statistics back in the early universe. It's just that over time, due to the natural dynamical evolution according to the wave function, the evolution of the wave function and the guiding equation, the particles end up distributed in such a way that all the context dependence exactly cancels out, and we end up with what appears to be a very fine-tuned situation, although really it is just a consequence of this natural evolution. So this is I think a really nice explanation, and to my knowledge, really no other mainstream interpretation of quantum mechanics has any explanation to offer for this phenomenon at all. So that this, I think, has not often commented on, but it is, in my view, a really big point in favor of the de Broglie-Bohm interpretation. This equilibration account also has one other really interesting consequence, because, as I said, if this is a correct account, it follows that in the very early universe, the de Broglie-Bohm particles were not distributed according to the wave function distribution, which means that some of the behavior in the early universe would have been not quite in accordance with the usual rules of quantum mechanics as we are familiar with it today. And that's really exciting because cosmologists now have a great deal of knowledge of how various ways in which we might hope to learn about what was going on in the early universe by making observations of things like the cosmic microwave background. So there's a pretty good chance that if this explanation is true and quantum mechanics wasn't obeyed in quite the usual way in the very early universe, we might be able to find signatures of that in the cosmic microwave background or some other cosmological phenomena. And this would give us a genuine experimental test for the de Broglie-Bohm interpretation. So this is my promised counterexample to the claim that interpretations never make novel predictions. In this case, the de Broglie-Bohm interpretation very much is making a prediction different from standard quantum mechanics. We don't yet have the data to either verify or falsify that prediction, but this is a really exciting possibility that at some point in the future we could have really good evidence for or against this particular interpretation. The other explanatory route I mentioned for these fine-tuning effects involved using teleological explanations. So that kind of route starts from the observation that the proofs of fine-tuning given by Cavalcanti works within the causal modeling framework, and the causal modeling framework assumes that all causal relationships can be represented as directed acyclic graphs. So that is to say, it's never the case that both A causes B and also B causes A. So the one natural way to get around this fine-tuning argument would be to criticize the assumption that all causal relationships can be represented in this way. So in a more general all-at-once picture where we have the laws of nature applying to the whole of history all at once, there is in general no reason why we shouldn't have both A causing B and B causing A. Because in that kind of picture, we have everything being adjusted all at once to optimize some quantity, rather than having the past cause the future and then the future does not act back on the past. So in this kind of picture, we can explain fine-tuned effects by applying some kind of global constraint, which is supposed to apply to the whole of history all at once, rather than sort of starting at the beginning and evolving forwards in time. And one obvious way to do that would be to just impose Gleason's property directly as a constraint. So we would say we require that our model has the property that context dependence is never observable at the level of the operational statistics. However, that does seem a bit ad hoc. That's probably a bit too easy and doesn't lead anywhere particularly interesting. So we would quite like to have perhaps a better reason why Gleason's property should be obeyed by the model. And in fact, there's a really good reason why Gleason's property should be obeyed, because if Gleason's property were not obeyed, it would be possible to send signals back in time. So to see that, suppose that we have two possible measurements, one with outcomes A, B, and C, and another one with outcomes A, D, and E. Then note that we can always split these measurements up so that first we make the measurement A, not A, and then we proceed to measure either B, C, or D, E. Now, if there were context dependence at the level of the operational statistics here, it would necessarily be the case that the result of our measurement, A, not A, would depend in part on our subsequent choice of whether to measure B, C, or D, E, because the probability of obtaining the outcome A would be different in those two different contexts. So allowing context dependence at the level of operational statistics would immediately allow us these sort of retrocausal effects or signaling back in time. And there are a number of reasons to think that signaling back in time is problematic and that the universe as a whole should not allow it. One type of concern that's been raised in this regard is known as bilking in the philosophy of time. So bilking refers to cases like in, say, the Back to the Future movies, where a person goes back in time and prevents their parents from meeting and thus prevents themselves being born. And thus prevents themselves from going back in time to do this in the first place. So bilking involves phenomena where we create some kind of loop which leads to paradoxes. So one way to make the argument that signaling back in time shouldn't be possible would be to raise the concern that if we had signaling back in time, then we could use it to perform these sorts of bilking scenarios, and we would thus get paradoxes, and the universe can't allow paradoxes, so signaling back in time must be impossible. However, what we are dealing with here in the contextuality case, we're not usually dealing with deterministic signaling back in time. Rather, we're dealing with probabilistic signaling back in time, where the probabilities where probabilistically the outcome of one measurement is affected by some future choice. And the bilking argument is slightly less convincing in the probabilistic case, because at worst what you get is a paradoxical type scenario where the paradox consists of a certain measurement having empirical distributions which differ from its theoretical probabilities. And it's not really clear that is genuinely a paradox, because one might simply argue that when we construct these kinds of closed loops, the usual theoretical probabilities don't apply. So the bilking argument is interesting, but perhaps doesn't get us all the way in the contextuality case. I myself prefer to make an argument in terms of determinism. So the idea here would be that if it were possible to send signals back in time, we could use those signals to create a closed causal loop where I would receive a message from the future. I would then send the content of that message to my future self. My future self would receive it and then send that message back in time to me so that I could receive it just in time to use it as the content of my original message. So whatever that message said would have just kind of popped out of nowhere. It would have no external cause. It would not be determined by anything. And so that kind of closed causal loop scenario is incompatible with determinism in a generalized sense. So basically the idea here is that by imposing determinism as a global constraint on our theory, we immediately rule out the possibility of signaling back in time, and it follows that Gleason's property must hold. So the idea is that determinism as a kind of teleological constraint entails that all the parameters of our models must end up being fine-tuned to prevent violations of Gleason's property. Finally, I want to observe that contextuality is also not the only fine-tuned effect in quantum mechanics. So it was observed some time ago by Wood and Spekkens that no signaling and non-locality also involve a kind of fine-tuning. So that's because in order to have correlations which are non-local in the Bell sense, but also non-signaling, you have to have your causal model very carefully fine-tuned such that all the non-local effects exactly cancel out to prevent you from using them from performing signals, from sending signals. So again, we have this situation where quantum mechanics seem to be fine-tuned. And again, for the same reasons as in the contextuality case, I think it's quite an urgent problem for us to try and explain why that is. Now, one explanation that has been offered in this sort of case by several important interpretations is that we can avoid this problem if we can find a way to say that quantum mechanics does not, in fact, involve non-local effects. So, for example, one way to do that is to suppose that we have retrocausality. So instead of non-local effects propagating instantaneously between different space-time points, we instead have a local signal that goes forward into the future and then back into the past to bring about this kind of apparent non-locality, which isn't really non-locality. But the problem here is that if it's possible to use retrocausality to bring about apparent non-locality, it would also be possible to use retrocausality to bring about apparent signaling. And so this kind of getting rid of the non-locality explanation doesn't actually deal with the fine-tuning problem, because we still have to explain why it's possible to use retrocausality to produce non-local effects to exactly this amount and no further. So this fine-tuning problem therefore persists even if we don't agree that quantum mechanics really is non-local. So on the other hand, equilibration explanations still work in this case, and that's exactly what the de Broglie-Bohm interpretation offers. One consequence of the equilibration account is that in the early universe, it would in fact have been possible to send superluminal signals. And that's one of the things that we might potentially be able to test and look for in the cosmic microwave background. And so some people think that's very exciting. On the other hand, some people are less willing to accept the existence of superluminal signals at any point in history. So there's kind of a division of opinions here on whether that's a feature or a bug, essentially. So to round up, I have argued that contextuality should not be understood in terms of Leibniz's principle, should not be understood in terms of Einstein's ideas. It should be understood as a form of fine-tuning, and we are therefore in urgent need of an explanation for that fine-tuning. And I've argued that the de Broglie-Bohm interpretation is, to my knowledge, really the only one of the mainstream interpretations to offer a strong explanation for that phenomenon. That I've suggested at some other possibilities in terms of teleological all-at-once models, but these are at present just ideas. No one has yet kind of come up with an explicit model that does that. So in the absence of further pursuing those ideas, I think the de Broglie-Bohm interpretation is in a really strong position here, and it offers a really interesting take on this particular phenomenon that other interpretations can't really compete with. So that's it for me. I do have some more that I can say about various mathematical frameworks for contextuality and what their significance is and how they relate to some of the things I've just said. But I think perhaps we should first move to some questions and discussion, and I can always cover that stuff later if people are still interested.
Thank you so much, Emily, for that presentation. It was definitely a lot of material that you managed to put in an hour. So thank you so much for that. Yes, so with that, I'd like to pass it over to the chair of this Beyond Bohm series, Shantina Sabatini, see if he's got any questions or comments.
Oh, thank you, James, and thank you very much, Emily, for a powerful presentation. Very interesting and deep. I'm particularly struck by the light it throws on the Broglie-Bohm interpretation. Most of your talk went over my head, and I assume that that's the case for other people in the audience. So allow me to ask you some very simple, very down-to-earth, minimal questions, starting with the understanding of contextuality. My first understanding would be like contextuality refers to meaning of, to measuring different quantum observables simultaneously. Is that correct? Or has it to do with like different preparation of the same quantum state?
So contextuality in its original form referred just to the Kochen-Specker type argument, referred to this idea that we should be able to associate quantum observables and regard them as definite properties of systems, which are either possessed or not possessed. It was later generalized by Rob Spekkens to this much broader idea that we shouldn't have cases where two processes which have the same statistics look different at the ontic level, and so that can refer to there can be different types of contextuality in that sense. There can be the preparation type, where we have two preparations that produce the same state but look different on the ontic level, or it can be the measurement type, where we have two measurements that are represented by the same quantum mechanical measurement operator, but are represented differently in the ontic model and in different measurements.
And in both these understanding, quantum physics is non-contextual.
According to both of those, quantum physics is contextual. Yeah.
It's contextual. Yes.
Yeah.
One more question. Like, what do you mean by averaging over ontic states?
So the way the ontological models approach works is that for any preparation that we do, we don't know exactly which ontic state we're going to prepare. We only have probabilistic knowledge, so each preparation is associated with some probability distribution over ontic states. And so the idea is that in order to calculate any predictions, we have to average over the ontic states according to this probability distribution representing our knowledge, because we never get to know the ontic state exactly. So the idea of the contextuality situation is that we might see that we have to have context dependence relative to any individual ontic state. But when we do this averaging procedure to calculate any predictions, all the context dependence exactly cancels out. And so we don't see that context dependence in the actual predictions, only in the ontological model.
You say exactly cancel out. And so that's what you meant by fine tuning?
Yeah, the fine-tuning concern is that it seems very weird and conspiratorial that these effects cancel out so precisely that we can never see them despite knowing they must be there.
And would this fine-tuning apply to the beginning of the universe, to the Big Bang, or?
So that's the thing we don't know. One possibility is that all the fine-tuning occurred in the initial state of the universe somehow, and everything was just very carefully programmed in the initial state so that things would always cancel out at all other times in history. That's one possibility. The equilibration type explanation that I was suggesting, that the Broglie-Bohm interpretation suggests, says that in the beginning of the universe, things were not fine-tuned and these effects did not cancel out. But due to the natural dynamical evolution of the system, things have moved closer and closer to the fine-tuned distribution, such that nowadays everything cancels out exactly, even though that was not the way things were initially at the beginning of time.
Okay, well, I will just let people ask their questions. And let me invite you, Emily, to be as down to earth as possible. You're speaking, talking for myself to a very ignorant audience.
Thank you, Shinten, and thank you, Emily, for that back and forth. Yes, so now we will open it up to all of you. As I said earlier, if you want to ask a question or make a comment, if you want to use the raise your hand function, which should be found at the bottom of your screen under reactions. Otherwise, physically raise your hand, and if I spot you, I'll call out your name, or just ask a question in the chat and I'll read it out for you. I can already see a hand up by Angelita.
Good morning.
Hello?
Yes, I'm having, I think I'm here now.
Yes.
Good morning. It's good to see all of you. And thank you so much for your words. I sat and let them wash over me so that my body, heart, mind, and spirit could understand what you were bringing to us this morning. And I'm coming to you from San Francisco, California, but a lot of my work in understanding what you are presenting to us was done in Tucson, Arizona over the last 30 years or so, when consciousness in the Consciousness Center in Tucson at the University of Arizona was just getting started. And so when we wanted to understand each other, we held salons, not unlike this one, except they were in person. And we came from our different disciplines, where there were many mathematicians that sat in our salon circles. David Chalmers sat at the circle in philosophy, and many other people, Stuart Amaroff, who's now working with Penrose. So my particular discipline was in indigenous ways of knowing and what might be called sacred science or native science. And they just called me the shaman, for shorthand. But what we decided is to call ourselves amateurs, so that in groups like this, where we are coming from different disciplines, we would all be amateurs in listening to each other in the Bohmian sense of dialogue, where we would disengage our infrastructures and our particular disciplines and listen to each other for truths. So I would like to offer that sort of as a follow-up to what has been said about down-to-earth conversations. It's not a dilution. It's not diluting or talking down to anyone. We all have particular aspects. So I wanted to share that because we've been doing this, those of us from different disciplines, trying to learn from each other for quite a while now. And I'm very, very appreciative of this series on Bohm, and I'm going to try to participate. My question to you is about something you said. As an amateur, identifying myself as an amateur, the universe cannot allow paradoxes. Now, I didn't quite get if that was your opinion, a result of your work, or a quotation of someone else's, but my question is to understand how you're using the word paradox in your presentation. Thank you, and thank you again for being here with us.
Thank you so much for your words. Yes, so I think the question of what is a paradox and can paradoxes occur in reality is a very interesting one, which is, people have a variety of opinions on. So I was using this in the context of approaches where we think of the universe as having laws which apply all at once to the whole of history. So in that sense, it's because everything is kind of decided at once, it is possible to just rule out, to say that the laws of nature just rule out paradoxes, because paradoxes in that sense can't accidentally occur if the laws of nature are because the laws of nature can adjust things to ensure that paradoxes don't occur. So by a paradox here, in this case, I would mean, for example, cases like the going back in time and preventing your parents from marrying type of situation, things which would lead to some contradiction somewhere. This is one of the problems with sort of possibilities involving time travel, for example, within sort of standard models where we think of things starting at the beginning of time and evolving forwards, because in that case, it's hard to see how you could rule out these kinds of paradoxes from occurring. Whereas if you have laws which apply all at once to the whole of history, you can ensure that your laws enforce consistency at all points, because they're not sort of constrained to look in only one direction, if that makes sense.
Thank you, Angelita, for that question. Beautiful words. Next question will come from the chat. Gary, don't know if you want to ask your question.
Sure. Can you hear me?
We can hear you.
Yeah.
So I've become very interested personally in the transactional interpretation, originally from John Kramer and subsequently modified by Ruth Kastner, because my inclination is toward a panpsychist understanding of existence, and that the reason for conscious agency is communication, and that at the heart of all of this is the issue of transaction. And I'm wondering, I've had an ongoing discussion with Ruth, and she's in the process of now editing a second edition of her book called The Transactional Interpretation of Quantum Mechanics, which I have here, The Reality of Possibility. And I think she has something worth considering. And I'm wondering, I'm sorry I missed the whole talk, and I don't know if you touched upon this, but if you did, I apologize. But if you didn't, I wonder whether you might be willing to comment on, what Ruth's ideas might have to say about the idea of the importance of context, and context, specifically with regard to communication and transaction.
Yes, so I think the transactional interpretation shares with a couple of other interpretations the nice feature of taking seriously retrocausality and the effect of the future as well as the past. And so I would class the transactional interpretation together with, say, the two-state vector interpretation and some other retrocausal approaches. I think these make sense within the scope of this kind of all-at-once approach that I've been discussing, because in this kind of all-at-once picture, you naturally have influences from both the past and the future. The past and the future are really equal on ontological level. And so there are various different proposals for how specifically you model the influence of the past and the future. And so the transactional interpretation is, I think, a really nice way of doing that. I don't think we have yet enough information to say which of these retrocausal interpretations is right, but I think definitely the transactional interpretation is doing something right in acknowledging the importance of both the future and the past, and how they have a sort of equal impact on the formation of measurement results.
Okay. Thank you. Thank you, Gary. Next question will come from Mary Elsa.
Well, hello. That's slightly answered my question, but I'm really interested in what you were saying about time, and how I loved your talk. Thank you so much. I'm a theologian and into systematics, so I don't really, but it's sort of similar language, quite interesting. Anyway, I'm interested in what you were saying about the retrocausality and how the potential of time, suddenly you bring in the dynamic of time, and it allows you to potentially track from what feels like a completely different dimension, because you have to split your maths or your mind out into more than one. I'm just very interested if you could just talk to me about what it's like when you bring in that different dimension, and how that allows I like the description of the wave you were talking about before, and I understand that whether that gave me an image of something constant with things allowing to be not constant around it. But I was wondering whether time does something like that, or I'm sorry for the beginner question, but I think you understand.
No, that's a really interesting question. Yeah, so I think physics has traditionally worked on this model where we think of the universe as being, something like a computer, which takes in an initial state and evolves it forwards in time. And kind of the reason why that's our model is because, that's the kind of theory we're interested in writing down. We're interested in taking the facts about the present and predicting the future. But for anyone who believes that, there's a kind of reality separate to human science and that the laws of nature might not be exactly the same as the laws that human scientists write down, there doesn't really seem any obvious reason to think that the true underlying laws of nature must take this forwards time evolution form. So I'm very much of my work is kind of focusing on what does physics look like if we get rid of time evolution and we instead think about theories which apply to the whole of the universe all at once, kind of like, the laws of the game of Sudoku apply to the whole grid at once rather than starting at the left and evolving towards the right. And the idea is that kind of the time evolution that we see can be kind of a perspectival effect from our position inside this grid rather than that's how the laws really work. And so the thought is that this kind of approach to a physics without time evolution offers us some really interesting possibilities for sort of explaining things that are strange about physics in new ways. And so that's kind of the idea I was exploring here in terms of these sorts of teleological explanations.
And would that mean that the different points that you found which were from different points in time were actually in relationship like a Sudoku pattern?
Yeah, exactly. And so in a Sudoku grid, for example, it's not the case that the value in one box causes the value in the other box and not vice versa. They equally cause each other. The effect is perfectly reciprocal, and that's the suggestion is that that's the same way it would work in reality. We don't have the past producing the future and not vice versa. It's all reciprocal.
That's wonderful. Thank you.
Thank you, Marielle. So for your question, next question. Well, actually, I believe Andrew, you've got a follow-up on this.
Okay, I'm really, really pleased that Chantana didn't understand a lot of this because he's massively clever, and I understood less. But I've got the answer to the last question and time, and that is, this morning I was walking down a lane here in Kent and it's raining, and I was fascinated by the stream by the side of the road going along and clumps of leaves having an effect on the future. And I thought philosophically that's what we are. There's this stream of constancy, and that I'm a clump of leaves and I have an effect on the future. So I thought, I wonder if I push one of those clumps of leaves, what it does to the future. So I removed it and the future flowed faster. But then I looked at the past, and the past was flowing faster because I've removed the leaves. So in fact, what we do does have an effect not only on the future, but on the past.
Yeah, no, I agree, absolutely. Everything is, as I say, is a reciprocal effect, right? The future affects the past and the past affects the future. It doesn't just all go in one direction. That's very much my view, yeah.
Excellent. Thank you.
Andrew. Great analogy. Next question will come from Steve.
Thank you. Can you hear me?
Yes, we can.
Okay. Very nice talk. Thank you very much. It's like Shantina, felt like it left skid marks on my head to a certain extent. I have a general question that you might be able to answer, and that is, have any string theorists offered any kind of an explanation of contextuality?
Steve,
I can imagine
maybe
ways
be
that
closer to your microphone.
but that's just my imagination. Has anyone offered anything? Oh, you can't hear me?
I don't know, Emily, did you hear?
I did, yes.
Oh.
I have
Okay.
never heard a string theorist talk about contextuality.
Did you hear the question?
Yeah, I did. I've never known a string theorist to talk about contextuality. I think in general, contextuality is most talked about inside quantum foundations, and it's not much it's not much discussed in other areas of physics, which is a pity, because as you say, it's entirely possible that string theory or some other theory of quantum gravity could perhaps offer some explanation of this behavior. But to my knowledge, no one has attempted to do that.
All right, thank you.
That's one of the reasons why I think, it would be nice if I think more physicists outside quantum foundations would perhaps try and get informed on these things, because I think, they could offer interesting contributions to these discussions.
Thank you.
Thank you, Steve. I can see a hand came up from tomorrow's speaker, Giuseppe. Would you like to ask your question? Or you're just muted at the moment.
Yeah, yes. Sorry, I do not want to. There were other people before me. Please don't.
No, it's fine. It's fine.
Okay. In any case, okay. Since you gave me, you see, talk by Emily has been very much suggestive to me, and I realized to many people, especially about this problem of time going forward and backward, which is also behind this translational idea of quantum mechanics. But in any case, the connection I would like to make with ontology, because Emily was talking a lot about ontological problems at the end of the story, I mean, is that we always move, all of us, within an ontological prejudice, namely that things can exist by themselves, which we never observe. We never observe isolated systems. We always observe systems in connections, interacting, in correlations with other systems. Dissipation is a key point of the whole story. And this makes any ontologism based on the idea that things exist by themselves something not tenable from a physical point of view. So if you go along this line, I mean, if you accept that Newton law, if you want, is a very rough approximation, because you only, in that law, you only have a second derivative of time, namely acceleration. And then all the problem with time reversal comes up, which does not, of course, in nature. Even in cosmology, in thermodynamics, of course, and in our human experience in all the biological systems. So there is another term in the story, which is a first derivative. In this sense, Aristotle was right. I mean, force for Aristotle were dependent on speed, which is a first order derivative. And then you do not have time reversal invariance. That symmetry is broken just for a natural fact, because things interact always. So this time issue comes in a beautiful way in the formalism of quantum field theory, but I would say also classical mechanics. If you consider Green's functions, you have advanced Green functions and retarded Green functions. You see, we disregard the one where time reverts cause with effect, because at that point we are lost in our everyday experience. But the point is that in our way of looking at the world around us, we always go back at our previous perceptual experience. So we go backward in time, and not in the sense that we go back in time, but in the sense that we fish from our background of a perceptual experience, and this operation is made in a beautiful way by our brain. And then on the basis of such past experience, we plan our future experience. So there is always this dialogue. The word dialogue was already stressed by somebody, I do not remember who, in connection with David Bohm, of course. So there is always a dialogue between backward in times and forward in times. And we live on the edge. The present is the surface of the mirror, of a time mirror, which is in front of us, because we see the world as our time reversed image, because it is because of dissipation. So, I mean, this is a comment, but many things that Emily was saying, even with the formal, how to say, elements, were suggesting to me this kind of a central problem, I think, in physics. We do not have isolated systems. And this, if you export this idea to everyday life, we go to the beautiful David Bohm teaching that things might be all related in some order which needs to be unfolded in our everyday experience. So that is my comment.
Thank you. Yes, I am in agreement with you that I think ontology needs to be understood relationally and as structurally rather than as sort of objects in and of themselves, and that this should very much have impacts on our views of time, and that one of the reasons why this kind of picture of the past as producing the future and not vice versa doesn't really make a lot of sense. And I love the image of the present as a time mirror. That's a really great image. That's very beautiful.
Thank you, Giuseppe. That was a really interesting question there. Really looking forward to tomorrow's session as well with you. Okay. The next question we'll take from Ronald.
Hello, can you hear me? Can you hear me? Okay. Two quick comments and a question. So probably, Emily, you probably heard of this. There have been experiments wherein quantum collapse is measured to have a delay. So if it has a delay, then it sort of proves the Bohmian-de Broglie theory that a particle has trajectory because there's delay in the quantum collapse, not instantaneous. So I think that's a pointer in the direction of the Bohmian theory. So 1 point for Bohm, the Bohm-de Broglie theory. Another comment is a possible application of the going back in time. There's this Libet experiment wherein they measured the neural response of a decision and the entailed physical response. So participants are asked, okay, tell me when I say go, clench your hand into a fist. So what they measured is they started clenching their hand into a fist before the decision to clench the hand into a fist. So basically, the muscles are preparing to clench before the conscious decision to clench the fist. Okay, so basically, some Iranian physicists suggested that there's a quantum going back in time of that decision to prepare the body to clench the fist. Mm-hmm. So, and they also presented the Bohmian theory in their paper of that Libet going back in time explanation. So that's possible. Anyway, my main question is, your theory, contextuality is related, I believe, to Bell's inequality theory, right? So basically, Bell's inequality theory is non-locality is a requirement for hidden variables theory. So the Bohmian theory is hidden variables, right? Yes. So non-locality, Bell proved that non-locality is a requirement for that. So how does that relate to contextuality? The way I understand contextuality from your explanation is that from the ontological going to the ontic, there's no fixed relation, right? So you have an ontological value beneath reality, and then when it manifests to physical reality, it's not really the same value, right? It has to be understood in context. So how does Bell's inequality sort of complements that that theory, complementarity theory?
Yes. So, well, for a start, Bell non-locality can be regarded as a form of contextuality because we can think of the measurement context as including the choice of both the local measurement and the measurement made by your partner who's making some measurement far away. And in that case, what we have in non-locality is just dependence on the measurement context. The fact that your measurement on this side depends on the measurement on the other side as well, which is part of the overall measurement context. So in that sense, non-locality is really just another form of this measurement context dependence, and Gleason, and in that setting, Gleason's property, which I talked about, is just the no signaling, the fact that we can't use this non-locality to send signals. So in that sense, non-locality and contextuality can really be seen as kind of two sides of the same coin, and we can we should ideally be able to explain these effects in the same way, which is exactly what the Broglie-Bohm theory does. It gives us an explanation for both of these effects in terms of this equilibration process.
I see. So basically, on the ontological level, on the quantum level, the causality can proceed independent of the ontic level. Is that? Yeah.
Yeah. So the ontic level, kind of the problem here is that the operational statistics that we see at the level of our measurements don't exactly reflect what's really going on at the ontic level. And so we must, for example, have non-local influences, but we can't see those directly because there's no signaling. And likewise, in the contextuality case, we know there must be some context dependence on the ontic level, but we can never see that directly in our measurements. So it's this kind of mismatch between what we know must be going on underneath and what we actually see, which is the problem, the fine-tuning problem that is in need of explanation.
But the ontic level statistically averages out to Newtonian
exactly.
causality.
The question is why does it average out in this very precise ways that all the signaling or all the context dependence exactly vanishes?
Okay, thank you, Emily. Thanks.
Thank you, Yonand. The next question will come from Mike. Is Mike there?
Are you talking to me, James?
No, it's Mike.
No, I didn't think so. I didn't actually have a question. I actually have a lot of questions, but I think I'm going to keep with the correspondence with Emily.
Okay.
Sorry, it was another Mike you had in mind. Sorry.
Yeah, sorry. No, Mike is here with us now. You're muted at the moment, Mike, but oh, you're still muted. Mike, you're still muted. We can't hear you.
James, which mic are you referring to?
I'm talking to Mike, who's called Mike's iPad 813.
Okay, right. I just want to be quite sure you weren't referring to me. Okay.
Sorry, Mike.
No problem.
Okay, there. Can you hear me?
Now we can hear you. Yes.
Okay. Thanks. Thanks for that medical operation. I'm back. James and Emily, there are 3 or 4 things floating around in my mind, and maybe you can blend them for me. The first is the relationship between communication as a general category and its relation to causality. I would, perhaps with Steve, propose that causality is a specific form of communication, and maybe looking at things that way changes the way we view them. Second thing is the centrality of time, which certainly came across to me in what you were talking about, and how if we make this change, that changes it as well, particularly marked by entanglement or non-locality and the simultaneous presence of the universe in some sense in all our acts, given that that time is fundamentally the form of action. And I just like you to kind of comment on this perspective.
Yes, so yeah, I think your analogy between causation and communication is very apt. I mean, obviously both communication and causation involve basically correlations, but the crucial point in both cases is that we expect that one end is kind of controllable, and one end we can manipulate and thus kind of bring about correlations that we want on the other end. So yeah, in that sense, communication is perhaps we use that term specifically when the cause is a human being trying to communicate a message, but the effect is the same, that we have a controllable end and non-controllable end, and when there are correlations between them. And that's nice because it then allows us to kind of think about both causation and communication in a more general sense, where it doesn't necessarily have to be going forwards in time. We could easily allow for the possibility of causation or communication backwards in time if we have cases where there are appropriate correlations and where the end which is controllable is the future end rather than the past end. And that's, for example, what we would have in the case I discussed if Gleason's property were violated, because in that case we would be controlling a measurement choice which affected, which would have correlations that with an event sometime in the past.
Okay, I'm wondering in the context of what you said, how you would integrate Bohm's notion of a hollow movement in terms of the flow of time or of communication.
Sorry, what was that?
Bohm had the idea, the crossing of the stone stepping across a stream, which you would get wet except when you didn't think.
Yes. Mm-hmm.
Okay, so and I'm relating that to the importance you assign to control here in your view, and I'm wondering how that aligns with the view that Bohm had of hollow movement, which is to let go of the control and just go with a movement emanating from the implicate order, making itself explicit in the moment.
Yes,
that makes sense.
Yeah, no, I think so the view I have of time involves kind of everything being determined at once in this sort of external sense, and so the control part is kind of a second layer that we put on that from our sort of local perspective, that we ourselves, being located in the universe, regard ourselves as having control over certain things and not over others. So this kind of the difference between the two ends of the correlations is always a perspectival effect in terms of what moment you're present in and what kind of psychological processes you have in terms of what you regard as being controllable. So the control is important to our concept of communication and causation, but not because that is kind of how things work at the most fundamental level, but rather because that is how we that's the overlay we put on our understanding of the world and our position in this sort of big all at once universe.
Okay, we'll see how that works out in time. Thank you.
Thank you, Mike. And sorry about the confusion. I've just realized there are about 5 mics on this call.
You woke me up, James. Thank you.
We'll take the next question from a physical hand up. Eddie.
Thanks, James. And I think there's only one Eddie, so I'm probably on a finger here already.
Definitely you.
Emily, thank you very much for your presentation. I have a sort of a long shot question, really, because of course, your word contextuality really grabbed my attention at the start, and then I would not be able to understand a lot of what came afterwards, which doesn't mean that what came afterwards wasn't deeply significant. But what I was wondering about was, and this is the long shot question, my interest in context is sort of to do with the issue of fragmentation that David Bohm was so interested in, that so much in the realm of communication, particularly in the media, the content is always seems to be fragmented from the context. So consequently, all sorts of distorted meanings keep emerging because there's very little attention to the wider context. So the question I have is, in your concept and explorations of the subject of contextuality, I just wondered, is there anything coming out of that that might shed light on why this propensity of humans to disconnect so much from context, and sometimes very deliberately, as certain dictators will do, is there any link between the quantum aspect of your understanding, or even a speculative link that might shed some light on why is content constantly being fragmented from context?
There's certainly, I'm not sure I'd say there's one explains the other, but there is kind of a nice analogy in that what we see in the quantum level is that when we look at the most superficial level, when we look at only the observations that we're able to make, we can't see the context dependence. So on the most superficial level, it doesn't seem as though the context matters because the context dependence isn't there in the operational statistics. So it's only when we try and understand at a deeper level, and we start trying to write down ontic models and try and understand the reality, that we see actually the context is really important, and we can't get rid of that. That context dependence will always be there in the underlying realist model. And so I think there's a kind of a nice analogy for what you're saying, because I think, in the media and so on, if you look at things on a very superficial level, it might seem like the context isn't important. But when you dig down a bit more, you find, as in the quantum case, that the context dependence is very important, and you can't just remove the context, and things won't make sense without it. So I think, there is definitely a quite an interesting analogy there, I would say.
Thank you.
Thank you, Eddie. Mark, I see you have your hand up.
Well, thank you. Thank you very much, Emily. That was hugely stimulating. I saw you speak in London as well a few years ago, and the EMQM was amazing. I was very amazed by your talk there as well. I just wanted to ask, the question is about bilking. You mentioned about bilking in your talk. I hadn't come across that term before, so I just wanted to ask a question about that. One of my interests has been about Bell's inequalities. I studied them a few years ago. I was looking at their there was many amazing experiments, as you know, since Alan Aspect, trying to close the loopholes that may exist, and the experiments have become more and more precise, and the distances have become further and further. And so, you got these entangled particles, and there's this non-locality thing. So my question is, well, in terms of like retrocausality and the idea of retrocausality, and bilking, this idea of bilking, like you're saying that bilking raises the issue of the the Back to the Future scenario, where you can go back and you can interfere with your parents so that you don't exist. And but I was just wondering, I suppose what I was wondering about was another interest of mine is synchronicity, actually. And for example, just before I came on this call, my wife texted me and asked me to measure the table in the kitchen. And then you started to talk. You started your talk talking about measuring tables. So I go, I think so. My experience with synchronicity is they tend to happen within quite a narrow time frame. And I was wondering, if there is a problem with bilking if it goes back to, say, 40 years ago. But within a narrow time frame, the tests of the Bell inequalities for the loopholes have been done within quite a narrow time frame, even though that time frame has been expanded. It hasn't been done over days or weeks or over months or years or over millennia. So I'm just wondering, like, is this bilking might work within short time frames? For example, the past and the future are somehow affecting each other, whatever the word is, over a short time frame, but maybe not in the longer time frame. Maybe it gets dissipated. It doesn't work over those longer time frames. That's kind of
So I think, in principle, the the difficulty, the bilking problem could occur on any time frame, provided that you had sort of some sufficiently well-defined process that was able to be composed to form some kind of contradiction. The thing about bilking is that there are two sort of conceptions of retrocausality, and bilking is a problem on the first one, but not the second one. So if you think of retrocausality in terms of a sort of two-state model where you have one state evolving forwards and another state evolving backwards, in that kind of picture, you can get bilking because you could have the forward state saying one thing and the backward state saying another thing, and that's going to lead you to contradictions. The other conception of retrocausality is more in the kind of all-at-once picture that I've discussed here, like the Sudoku grid. Because in, say, the Sudoku grid, you know, the squares on the left affect the squares on the right and vice versa, but it's entirely reciprocal. And you can't get contradictions from that kind of retrocausality because everything is just being adjusted together. So if we're thinking about retrocausality in that kind of all-at-once picture, we don't have a problem with bilking anymore because it's part of the way the laws of nature operate is that they resolve any contradictions and everything is adjusted to make it make sense. So I think for me, it's really important that when we talk about retrocausality, we distinguish between that first type and the second type, because the first type does lead to a lot of paradoxes and problems. The second type doesn't have those problems, and I think is much more convincing as a kind of model for physicists.
Thank you.
Thank you, Mark. Alan, would you like to ask your question?
Yes, thank you, Emily. This is really a fairly basic question to sort of something I've been curious about. But we know that, or it's believed that 95% roughly of the universe consists of dark energy and dark matter. Dark energy about 70%, dark matter about 25%. And I remember hearing a talk where even the terms dark energy and dark matter were described as being highly misleading because they imply we know far more than we actually do.
Yes.
And I think the speaker was actually suggesting we call them Bill and Ben to reflect how much we know. So what I'm curious about, my question is there an assumption that quantum theory will apply to dark energy and dark matter? Or a further question is there any conceivable role for dark energy and dark matter in interpretations of quantum theory? Thank you.
Yes. So I think people have made various proposals for what the origin of dark matter and dark energy could be using quantum ideas from quantum mechanics and from particle physics and so on. So in that sense, I guess the hope for those people is that using standard quantum mechanics and postulating some unusual type of particle will be able to account for what's going on there. The alternative, of course, is that we do something much more extreme and say move to something like a modified gravity model where actually there isn't any dark matter. It's just that the laws of gravity work differently on very large timescales. So I'm not sure that any current interpretations of quantum mechanics say much about dark energy or dark matter, but I think that's perhaps obviously one of the big problems for quantum mechanics and the interpretations of quantum mechanics is to understand how to reconcile quantum mechanics with gravity and to do quantum gravity. And I guess one of my hope in working on the interpretation of quantum mechanics is that better understanding quantum mechanics will also help us better understand how to do quantum gravity. And I think probably the reason we've had trouble with that so far is that we never fully understood the sort of conceptual basis of quantum mechanics. So my hope in the long term would be that getting the interpretational stuff right would help us do quantum gravity properly, and that the correct theory of quantum gravity would also help us understand the true nature of dark matter and dark energy. But that's a sort of pipe dream at the moment.
Thank you.
Thank you, Alan. We'll take the next question from Theo.
Hi, everyone. Thanks, Emily, for the talk. Very, very interesting. Yeah, I was especially fascinated about this concept of averaging out or fine tuning. It's kind of new to me. And yeah, I found interesting this introduction of the equilibration process, which sounded a little bit like trying to answer a question with another question, but then you're like, okay, how do we find out about this this equilibration process? And so I don't really have a specific question, but it's most actually, if there was anything, would be like, how are there any ideas around how to prove or misprove this existence of this process going on?
Yeah.
And yeah, and then this is really like a naive intuition, or when I think about universal processes leading towards an equilibrium, I think of the second principle of thermodynamics somehow, and entropy like leading somewhere. And I wonder if there's any correlation with this.
Yeah. So there is a relationship with thermodynamics in that one of the Valentini is one person who has made this equilibration argument, and kind of the way in which he proves the approach that the de Broglie-Bohm particles approach the fine-tuned distribution in the long term. He's using methods really quite similar to the ones that Boltzmann used in Boltzmann's H theorem, which he was trying to use to demonstrate the validity of the second law of thermodynamics. And Boltzmann's H theorem is actually where it's now understood that proof is not quite right for some fairly complicated reasons. But it's interesting that Boltzmann's methods kind of do work correctly, we think, in the de Broglie-Bohm case, and that we do see this kind of approach to the fine-tuned distribution. With regards to proving it, yes, absolutely. There is definitely hope that we would be able to prove it, because if this equilibration account is true, it follows that in the early universe, stuff like, if for example, we have no signaling now because of equilibration, it follows that in the early universe, no signaling didn't hold, and thus we would, for example, have been able to have superluminal signals in the early universe. And that's the kind of thing that we should hopefully be able to observe in cosmological observations and the cosmic microwave background and so on. So if we do see those signatures, and I know that people are looking for them, that would be really strong evidence for the correctness of both de Broglie-Bohm and the equilibration account.
Great, thank you, Theo. Todd, would you like to ask your question?
Yeah, actually, I think the previous question answered and the response to that quite closely, getting a first wonderful dose of equilibration. I guess cosmologically, in the microwave, the gravity background, we're looking for things that in past in time where the fine tuning is not as great as we're witnessing now. Is that looking for, is that an empirical strategy for sort of proving or giving credence to the de Broglie-Bohm interpretation? Is my initial understanding?
Exactly, and I think Valentini and others have made some quite specific proposals for what effects we should be looking for, and I think we haven't yet been able to make the right observations. But I think we do have a reasonably clear idea of what kinds of observations we could make that would provide support for this.
All right, thank you.
You, Todd. Kurt Sharon, you do have your hand up.
Yes, thank you. Good, excellent, Emily, in the presentation. I did notice in both your bibliography of your new book and then your comments here that you're well aware of Pussy and Leifer and Aharonoff's work on the thing, which I work with a lot.
Oh, lovely.
And it's very interesting in how that kind of resolves a lot of paradoxes. The paradoxes being the sniffing of where to look, you might say. And recently, the new PNSA papers that show true top-down causality and what they call N levels of non-locality and counterparticles ends up resolving a lot of these things, or at least suggesting that it's a useful area to continue progress. And there's a way to bridge that into some ideas about how perception, presence, and awareness are part of a normal extended realism picture, okay? So anyway, I want to know if you have any comments on that, because I see you're really up on that. I'd love to hear what you're thinking about it.
My own work mostly focuses on approaches which kind of move away from the standard time evolution picture. So I think these sort of the two-time type approaches and retrocausal approaches are very much the kind of thing that I am interested in, and sort of the idea of that realism can mean more than the sort of very standard mechanistic picture of the universe as a computer that evolves something forward. We need to be much more general in our ideas about what sort of realism could look like and what how the laws of nature could look. So yeah, very much I'm very interested in particularly retrocausality and other such approaches. Yeah.
All right. Well, thank you so much. Look forward to seeing you sometime. Bye.
Thank you for your question. Oh no, Basil, is that a hand up? You're just muted at the moment, but
Yeah, is it a hand up or a goodbye? I'm not sure. Has everybody who wants to ask questions of Emily asked the questions? Because I've been, dare I say it, an expert in the Bohm-de Broglie theory. I've got many interesting questions to ask Emily. But Emily, first of all, thank you for that talk. It's brought me back to stuff that I was interested in a few years ago. I have moved on a lot. I also noticed that you hope that by understanding quantum mechanics at this fundamental level, we'll get a better idea of how to quantize gravity.
Yes, yeah.
Bloody good luck with that.
Well, yeah. I'm not saying I'll do it myself, but
that is what I was hoping to do when I was working with David Bohm and Roger Penrose at Birkbeck way back. So I'm afraid I'm a total failure because we've got nowhere near understanding how the thing works. One thing I was interested in what you were dealing with, I mean, a lot of things that I was interested in, but particularly on the asymmetry, the Einstein point of view. What was it you were trying to say there? I didn't get it clearly because I have a feeling I might be going in the opposite direction. So I'd like to get it clear what you meant by that.
Yes, well, what I was saying was that many people will invoke Einstein's comments here it has been suggested by some people that the thing Einstein had to say about asymmetries is also the motivation for what is problematic about contextuality. The idea is that contextuality is bad because we have an asymmetry which is not inherent in the phenomena. And my comment was simply that this argument doesn't really work very well because what we know from the proofs of contextuality is precisely that whatever contextuality is, it is very much inherent in the phenomena. It's totally unremovable. So, in Einstein's case, he was pointing out that absolute space could be removed without losing any empirical content. But we know from these contextuality proofs that contextuality certainly can't be removed without losing empirical content. So it's not, in my view, a useful way of thinking about what contextuality is.
Okay. No, thanks. No, I got hold of the wrong end of the stick, so I can't make any more comments. Because I mean, I am going to talk. Am I going to talk on the 2 weeks' time? No, next week?
Next week, Basil. Next week you're talking.
Thank you for reminding me. But I will be saying a lot more then, so I'll keep quiet now.
I look forward to it.
Great, thank you, Basil. I think we have maybe time for another question, maybe two. Niels, sorry, I didn't see your physical hand up.
Okay, yes. Okay, I thought, Emily, you touched on something very important, and that was the idea that everything moves in parallel. So, and that's the same that Ian McGilchrist would talk about the brain and the right hemisphere. That is the parallel that can swoop over the wide system and understand that. I was thinking you were talking about going backwards, but there's another way of looking at it, that we are always in the present, we are always in the now. So if you have a picture of the now, that could be a picture of all the opportunities for the entire system to move on. Then you can move on and into the next present. I have some evidence for this. I'm not a physicist. I was good at physics, and I loved the split problem. I did some calculations on that as a student, and my tutor came to me, and he was puzzled by the way I have solved the problem. And so, but I'm in another sphere. I've been doing transportation modeling. If you imagine you've got pedestrians moving in a complex system, and inevitability directed me to this idea of the now and the movement in very small. In that way, you are always optimizing it. In a way, it resonates with what we call the least action kind of paradigm. Yes, and so since I found this, I actually found an algorithm like a digraph thing, but for transportation, the geometry of transportation, and it has been very successful. But the community of transportation modelers don't get it, so they don't like it. But it really plays well in with the idea you brought to light. So I'm still hoping to be able to have an impact with this kind of system.
That sounds very interesting. Yeah, I think definitely one big, probably the most important open question for physics is kind of the way in which we understand time, and I think it's pretty clear that our naive understanding of it that physics has used for many hundreds of years isn't really working anymore. So the question is, what should we move to? So this kind of new approach to time is exactly the kind of thing we need to be looking at and understanding.
Yes.
How else can we think about time?
Yeah.
Thank you, Niels. So we've got about 2 or 3 minutes left, so I guess we should start closing the session.
Yes. Okay.
Santina, do you have any final remarks to give us?
Yeah. Thank you very much, Emily. I think the liveliness of this conversation at the end is a witness to the impact of your presentation. It makes me feel, amongst other things, that this problem of time is still very much with us and very alive. We had a conference on time, 2018, was it?
I believe so, yeah.
Yeah, something like that. Seems like we're ready to have a couple more. So thank you, Emily, for waking up this sleeping demon of time.
Thank you, Shantina. And yes, Emily, thank you so much for your session. Do you have any final remarks for us before we go?
Thank you, everyone, for your questions. It's been a really interesting discussion. I'm so glad that you found the talk interesting and had given these people new ideas and things to think about. So thank you for all this discussion.
Okay. Thank you, Emily. And yes, I hope to see you in Paris soon, when finally we'll be able to meet in person.
Great, yeah.
Great. Well, thank you, everyone, for joining us. It's been a fantastic session, fantastic turnout. Just before we go, I'd like to invite you all to tomorrow's session. You've met him already, Professor Giuseppe Vitiello, who will be discussing the brain and its mindful double. In the meantime, if you want to contact us, you can visit our website, and we've got a contact us section, or you can write to us on social media, Facebook, Twitter, Instagram, or you can just email directly at james@pariscenter.com to contact me, or eleanor@pariscenter.com to contact Eleanor. Thank you again for joining us, and we'll see you again soon here at the Paris Center.
Thank you, James.
Thank you, James.
Thank you, James.
Thank you.